At Skayl, our name says it all. We provide scalable integration solutions. As systems have become larger and incorporate components from many vendors, often spanning multiple technology generations and software stacks, our industry must adopt a different integration strategy. The principals at Skayl have decades of aerospace and defense experience. We've seen how things work and how they don't. A few things that don't work are relying on common message sets or common transport protocols. These may be fine for a distributed application, but not for a long-lived system of systems. Messages change, operational needs expand, data producers and consumers come and go. Instead, we approach the problem by moving up an abstraction level and use a data architecture to document the communicated information in terms of its fundamental semantics and context. The specific messages are just views, like in a database, that are tailored for each component. Coupled with the layered, data-centric software architecture, this enables a fundamental shift from application-driven integration to infrastructure-driven integration. The Navy has grappled with this integration challenge. While we can build amazing systems, it is a slow and expensive process. This quote sums up the need. "Velocity is my combat advantage." That's from James Gertz, who is currently performing the duties of the Undersecretary of the Navy, in a comment on the importance of quickly fielding solutions for SOCOM. If we cannot quickly integrate new capabilities into fielded systems, we will lose that advantage. And of course, there are efforts to solve this problem. Recently, there's been a lot of attention on DevSecOps. It's a big part of the Navy's integrated combat system and the Air Force's Platform One initiatives. DevSecOps is an approach with origins intended to bridge the gap between developers who write software and the administrators who deploy the operational product, and it can help. Just as commercial off-the-shelf operating systems and middlewares are leveraged by defense programs, commercial development processes and tools can add value too. However, in some important ways, the commercial and defense industries are different. What's the oldest app you can run on your phone? Most consumer and enterprise software has more control over its environment. Of course, everyone's using the latest version, because that's all that is supported. Of course, the data is in one format, because the server is controlled by one company. These are anti-patterns for defense, as the government has seen the pitfalls of vendor lock-in. Commercial DevSecOps often focuses on the syntax of data and the mechanics of build and deployment tools. This is necessary, but not sufficient to achieve true interoperability. We will elaborate on this idea in an upcoming paper for the American Society of Naval Engineers Intelligent Ships Symposium, titled Achieving Warfighting Lethality via System and Semantic System of Systems Model-Based Engineering Integration. The place that this SBIR focuses on is automating integration. It's not just generating code, although that's important. How is it tested? How is it certified for safety or operational use? We've taken existing combat system models and enriched them in a few ways. First, we've augmented the syntax. It's not just an integer, it's a track ID. It's not just a tuple of numbers, it's a position. We've also identified logical measurements and coordinate systems. Second, we've taken behavior expressed in sequence diagrams and crafted it into a machine parsable form. Instead of just a text field, we link to a specific data type sent or received. Instead of just a natural language description, we codify the specific state driving one behavior versus another. Importantly, none of this is tied to a specific communication protocol or test infrastructure. For the purposes of proving out the method, we use an existing test harness and our Phase transport service, but the approach itself is generic. This shows the value of a data architecture that is based on fundamental physical and domain concepts instead of purely syntactic documentation such as IDL or XSD. So, what do we get from these models? By rigorously linking all these concepts, we allow computers to interpret and leverage the information. When we know that fields in different messages contain latitudes, except one uses degrees and another uses radians, we can algorithmically generate a conversion. When we know that a data type contains a sensitive position, we can trace its data flow to identify exfiltration threats. When we can evaluate a component's expected output given some input, we can generate tests to validate it. All of this increases integration velocity. We reduce handwritten code and thus the chance of errors. We reduce data ambiguity and thus the chance of misinterpreted messages. We reduce changes to business logic and thus the number of components needing re-verification. We increase test coverage. We increase the data validation within the infrastructure, thus catching incorrect data sooner. We increase static analysis that can be done, thus finding integration problems sooner. We are nearing the end of the Phase 2 base of this SBIR, but Skayl is involved in many efforts related to integration. An early SBIR with NavAir proved out the core ideas of a configurable transport service. This advanced to a Phase 2 that focused on model manipulation and management. This is crucial as artifact generation relies on good model inputs. This work has also transitioned to the Army, where we are addressing needs such as airworthiness certification, fast development of FACE software components, and core infrastructure capabilities. Skayl was the contract prime in the role of architect on the Army's JMRTD Mission Systems Architecture Demonstration Capstone project, which explored architectural methods, tactics, and standards for integration flexibility within the Future Vertical Lift platform. We are also involved in several standards organizations, including the FACE and SOCIA consortiums. 3 features highlight the benefits of this project. Semantic data models can document the allowed ranges of data values, not just at the message field level, but at the logical level. We don't have to say that every instance of longitude in a message is between -180 and 180 degrees. Instead, we relate those fields to a measurement whose coordinate system is limited to that range. A different system could instead have a range of -pi to pi. A second feature is a covering array tool created by NIST that efficiently creates test cases with interesting parameters. This is useful because many errors are only triggered by a combination of inputs, like a bug that only happens crossing the international date line on February 29th. Data models provide the inputs to this tool, so to generate inputs with semantically interesting values, such as boundary conditions, is easier. A third related feature is using data models to generate validity checks within the communication infrastructure. A future area we plan to investigate is to use semantics to detect inconsistent data, such as a reported position that changes faster than a reported velocity would allow. Note how the same model content, the semantics and context, is being used for several different purposes. We aim to reuse instead of re-implement. By enabling more robust testing, we get faster and more reliable integration. We plan to use the Phase 2 option to apply these integration techniques to the existing combat system. Although the approach is generic, it still must be incorporated into current processes, technologies, and infrastructures. We are working with the PLA maintainers to understand current software development and deployment challenges, and we have a CRADA with NSWC Dahlgren to get feedback on our products. Thus, we are well positioned to fit into the Navy's transition to an integrated combat system. Phenom is our software-as-a-service web application for data modeling and infrastructure generation, which has both government and commercial users. It is sold as a subscription, similar to other licensed tools in development and integration pipelines. Sync, which stands for Configurable Infrastructure Capability, is our transport service aligned with the Phase technical standard. Although we are currently focused on aerospace and defense, we believe that industrial, commercial, and enterprise systems will face the same core integration problems as their systems become larger and more complex.